Have you ever stopped to wonder how one material, say aluminum, can be both super flimsy and ridiculously strong? I mean, really think about this for a second. You can crush an aluminum soda can in your hand, but the wing of an airplane, also made from an aluminum alloy. And that thing has to handle these incredible forces, holding up hundreds of tons at 35,000 feet. It's the same basic stuff. So what is going on here? What's the secret? Well, the answer is this amazing process. It's called heat treatment. And what's wild is that it completely transforms the properties of a metal without changing what it's made of. It all comes down to a super precise recipe of heating and cooling. Okay, so just like any great recipe, whether you're baking a cake or forging a sword, heat treatment follows a few basic core steps. No matter what you're trying to achieve in the end, the whole process always starts with this universal foundation. You can think of it like a simple three-act play. First, you heat the metal up in a furnace to a really specific temperature. Then, step 2, you let it soak. And finally, you cool it all the way back down. Now, heating and cooling, that makes sense, right? But that middle step, soaking, what's that all about? Soaking, this is where the real transformation starts to happen. See, it's not enough to just get the metal hot. You have to hold it there, letting it kind of cook at that exact temperature for a precise amount of time. This gives all the atoms inside the metal a chance to, move around and rearrange themselves into a brand new structure. This step is all about patience and being super, super precise. But here's the real kicker. While the heating and soaking set the stage, it's that final step, the cooling, that's the director of the entire show. The way you cool the metal, how fast or how slow, that's what decides if that hunk of aluminum ends up as a flimsy soda can or a wing on a 747. All right, so let's check out our first recipe. Let's say your goal is to make a piece of metal as strong and as tough as it can possibly be. To do that, you're going to follow the hardening recipe. With heat treatment, you're almost always shooting for one of two totally opposite goals. On one side, you've got hardening. That's all about maxing out its strength, making it tough and resistant. But on the complete other end of the spectrum, you can soften it. And why would you do that? To increase what's called ductility, basically making it way easier to stretch, bend, and shape without a cracking. And to get these completely opposite results, you guessed it, you use opposite methods. To make metal hard, you have to cool it down incredibly fast. This process is called quenching. You've probably seen it in movies. The blacksmith plunges a glowing red sword into a barrel of water. That's quenching. But for softening, you do the exact opposite. You cool it down as slowly and gently as you possibly can. So why does cooling it down so fast make it strong? Well, what's happening is you're essentially freezing the metal's internal atomic structure in this really high-energy kind of stressed-out state. All that internal tension is what we feel as strength and hardness. But, and this is a big but, there's always a trade-off. All that stress also makes the metal more brittle, which means it's much more likely to just shatter instead of bend. Okay, so what if you don't want a brittle, super strong metal? What if your job is to shape it into something complex? Well, that's where our second recipe comes in. This is all about creating flexibility, and we do it through a process called annealing. Annealing is basically the gentle, zen-like counterpart to that violent quench we talked about with hardening. By heating the metal up and then letting it cool down very, very slowly, you give its internal structure time to just relax. It settles into its most stable, lowest energy state. And that process removes the stress and makes the material way more workable. Here's a good way to think about it. When you work with metal, bend it, roll it, hammer it, you're building up all this internal tension. We call that residual stress. It's kind of like your muscles being sore after a tough workout. Annealing is like the deep tissue massage for that metal. It lets it fully relax, getting rid of all that built-up stress so you can go back and work on it some more. All right, so we've gone through our two very different recipes. One was fast and furious, the other was slow and gentle. So let's take a look at the results. What have we actually created? What are these final properties called? This really boils down to two key properties, two opposite outcomes. First up, we have ductility, which is what you get from annealing. Think about a paperclip. Its ability to bend and be reshaped without breaking, that's ductility. The exact opposite of that is brittleness, which is that trade-off you get with hardness. Think of a dry twig. You try to bend it, and what happens? It doesn't bend, it just snaps. That's brittleness. And this table here, it sums it all up perfectly. For hardening, you use fast cooling. The result? High strength, but low ductility. For annealing, you use slow cooling, and you get the opposite, low strength but high ductility. See that? It's a perfect inverse relationship. You push one up, the other goes down. And that right there is the fundamental lesson of all of this. You can't have your cake and eat it too. You just can't get a material that's both ridiculously strong and super flexible at the same time. It's always a trade-off. An engineer has to pick the right recipe for the right job. You need strength for that airplane wing, but you need ductility for the soda can. So you might be wondering, how in the world is all this precision actually achieved? Well, it all happens inside these highly advanced high-tech furnaces, where every single little variable can be perfectly managed and controlled. To get the perfect recipe, you need absolute control over everything. We're talking about incredibly precise temperatures, often measured by things like pyrometers. We're talking about the exact timing for that soaking period, right down to the second. Even the atmosphere inside the furnace itself is controlled. Sometimes it's a specific gas, sometimes it's a total vacuum, all to prevent any contamination. And of course, the rate of heating and cooling, that's the big one, is controlled with insane precision. And look, this isn't just some obscure industrial process. This incredible level of control, this is what allows us to build basically everything in the modern world, from tiny surgical tools to massive spacecraft. The ability to write and execute these material recipes is, without a doubt, a cornerstone of modern engineering.